Greetings, my name is John Gabriel, and today I'm going to be discussing an article by a couple of Greek academics who should have known better, but don't. And sad to say, this is the case with not only Greek academics, but all mainstream mathematics academics. So I'll go through the article and provide my commentary as we go along. So let's begin. Now, this article was written by two gents, one called Voskoglu and the other one Kosivas, or Kosivas, however you pronounce that. And the topic is on analyzing students' difficulties in understanding real numbers. Now, let's see. Let's go through the article. So, whenever I see uh, mainstream academics articles that have the expression students' difficulties in understanding, the first thing I look for is what follows naturally. Okay. In this case, the subject is about a non existent object called a real number. So already I know that the article is going to be a bunch of crap because there is no valid construction of real number. It's an ill formed concept that arises only in dysfunctional minds. Okay. It doesn't exist as a well formed concept. Now, when one thinks about these things, you have to ask yourself, how can one understand a concept that is fundamentally incomprehensible due to its ill-formed definition? Think about that. Okay? It's just about impossible to teach a concept if you don't understand it yourself. So one would at least think that the authors would start with a definition at the very least, but they don't. Okay? And you can see my article here called On Dietic Cuts on my academia site, this site here, and see why there is no such thing as a real number and no valid construction. So the empiric approach, excuse me, the empiric approach, we should never have in pedagogy something like an empiric approach. Never. Okay. We don't do things by experimentation. We do things through careful planning, through careful thought. At least that's how I do things. That's why when I discovered the new calculus, I wasn't guessing in the dark like Isaac Newton and Leibniz and all the morons who came before me. I knew exactly what I was doing because I think clearly and I think using well-formed concepts. Now notice as you go along here, there are so many citations and no substance whatsoever. Okay, no substance. If you read this, you'll yawn about 100 times. And citations are necessary in these so-called scholarly articles or publications because without them, they're supposedly not erudite or scholarly. So then the author says another characteristic of rational numbers that possibly affects negatively their understanding is their multiple representations. Actually, there's nothing that is difficult about understanding these representations. And although the measures are equal, the processes are strange, or the processes are different. So, look, when you write, for example, the ratios, let's go to a notepad. When you have ratios like that, and then like that, and this is equal to this, okay? So when you have ratios like this, the measure of this ratio is 1/2. Why? Because the ratio has quotientness. And in Greek, that's called piligotita, something which moronic Greek professors have never understood. And by the way, they should have if they understood Euclid's elements, but they didn't. Book 5, definition 3. Okay, that's your homework. My message to the authors, if they're watching that, you go back and you study that definition to find out what piligotita means. Okay, so this means that we're taking this ratio, this magnitude here, and we're measuring it with one equal part of two. Okay, so this here is the antecedent, and this is the consequent, and its measure is simply the enumeration of these parts. It's the name that we give to the number. Okay, it's the name that we give to the number. Similarly, if we've got a consequent like this, then we're using two of four equal parts to measure it, okay? Now, although these measures are the same, a half is equal to 2/4, they aren't done the same way, okay? Because here we're enumerating in terms of two equal parts, and here in terms of four. And by the way, since the antecedent is what is actually the important part of the ratio, and from which the number depends on its derivation, this antecedent is not equal to that antecedent, okay, which is not equal to this one, okay, where these are equal. So can you see the problem there? Yes, there's a problem. So these authors did not understand any of these things. So basically, they run around in circles and think that the students are having problems when in fact they're the ones with the problems because they've never understood and they've never been able to teach it correctly. Now, one of the next quote I want to deal with says, it seems that the concept of rational numbers in general remains isolated from the wider class of real numbers. Well, that's nonsense, what Moseley and Tupler think. And of course, rational numbers, with rational being redundant, okay? It's not necessary. Numbers are rational, and rationality implies number. Um, these numbers have nothing to do with real numbers because real numbers don't exist as well-formed concepts. Period. And I'll explain that in a moment. So the only people who are confused about nonsense like this claim here are those who are math professors and teachers. All of them are incorrigible morons. And you can get an idea of why that's wrong by studying this article down here, Realization and Development of Number in one page. Okay, so in one page you can understand number. Just go to this link. That's it. That's all you need to do. Realization and Development of Number on my site here. Here it is. Well, let me go to another one. That hasn't been updated yet. So if we go to this one here, you'll see it in a moment. Okay, so here it is, Realization and Development of Number in one page. This is the document you need to read. Right, so it seems, then they're right, it seems, however, that apart from the incomplete comprehension of rational numbers, there are also other obstacles that make comprehension of irrational numbers more difficult. But it's absolute rubbish because rational numbers are defined perfectly well without any other concept, especially an ill-formed concept like irrational numbers, all right? And of course, irrational number is an oxymoron because if you say irrational number, it's like saying irrational rational, which doesn't make sense, okay? And so these Greek authors should study my article at this time called Gabriel Arithmetic Without Numbers, a method based on Thales proportionality theorem. So in this article, I explain to you how you can do the four basic operations of arithmetic to 100% precision using an ingenious method that only I could come up with because I'm a genius and you're not. So I'd like to harp on that because a lot of you are incorrigible stupids who leave dumb comments in the comment section. Please hold your 2 cents, you morons. So the next thing is that they say fractions and numbers and irrational numbers, and they're totally confused, and they don't know how we got the theory of fractions. Well, again, my article, Gabriel Arithmetic, and this article here, Theory of Fractions, from Book 5, both go into extreme detail about these concepts. And I'm yawning because at this time I've discussed these things before, and to me they're boring, but to you they're new. Now, another thing that's very irksome is further Sirotic and Zaskis focusing on the ability of prospective secondary teachers in representing irrational numbers, irrational rationals, as points on a number line. Now, there's something terribly wrong with that expression, by the way. Not something, a lot of things. Okay. So, first of all, a number line does not consist of points. Okay. That's a fallacy that has been perpetrated far too long. It doesn't consist of points, and you cannot construct or reify a number line unless three things are in place. To find out more about that, you need to read my article on academia called "Is the Number Line Real?" And by the way, why can't you say that a line doesn't consist of points? Okay, so you've got a line now. Why doesn't a line consist of points? Because a line is a distance between 2 points. Okay, there's nothing in between there. We only draw that line to show that that's the shortest distance. We could have drawn a line like that. Okay, but there's nothing there. That's just representative of a distance. There are no points. Now, when we talk about points, it's the same as having a road, okay, and a little sign on the road. 2 miles, okay. So if you start here and you're over here, then you've covered a distance of 2 miles. But this poster here is not part of the road, okay. This is more like what a point is, not an actual imaginary little circle as your moronic and incorrigibly stupid math professors teach you and your teachers. So I bet you didn't know that, right? Right. A line does not consist of points. Very important. If you don't learn anything else, then learn that at least. So the next thing is, they dive right into decimal representations as if there's something holy about these things. There's nothing holy about those. Okay. And if you look at a number like a third, that's a well-formed rational number. When you try to represent it in base 10, you fail because of the most important number theory. Here's a link to it. Here's the link, which these moronic people never learned. Okay. You cannot represent a third in base 10 because 3 is not a prime factor of 10. Okay. So it needs to be either 2 or 5 to be representable in base 10 because there is no such thing as an infinite decimal expansion. That's just utter garbage. There's no infinite anything. Infinity is a 100% bullshit concept. So then we come now to the part of, this is also funny, where they say the intuitive difficulties with the perception of incommensurable magnitudes and the property of the continuum of R. Since that idiot George Cantor came on the scene, mathematics just went down the sewer faster than you can imagine. Okay, so they don't even understand these things. And because they can't be understood, they're garbage. So now we come to the part where they're about to show what their research has revealed. So here they say the failure of many students to recognize that all given numbers were real numbers was really impressive. The failure, actually, I would have called it the opposite. Those students must have been extremely smart because they weren't brainwashed by mainstream dogma, right? So And then we have the descriptive statistics to give the illusion of scholarly research and some actual numbers, maybe a normal distribution coming up. Well, almost normal, right? Let's see, what else? Maybe some hypothesis testing. No, I think they skipped it in this article. I think they got lazy. All right. So at this point, we are done with the descriptive statistics and the scholarly bullshit. Time for these authors to reveal their new research. So these Greek authors used the word qualitative. Qualitative. That's quite a hard word for a Greek to know, you know. Why do I say that? Because I know a lot about Greeks. Right. So we get down to the section of where they start asking the students questions. So here they said, why did you answer that minus 5 square root of 5 over 2 is a rational number? And the student said, because it is a fraction. That's entirely logical because you can only write P over Q if the measure of the ratio P to Q is possible. So that's what the student thought. Okay. And students think of square root 5 as a number constant, which is exactly how it's used. So they say in this case we have a classical misinterpretation of the definition of rational numbers. No, that's false. That is exactly how rational numbers are defined. Okay. In other words, let me repeat. Let's clear this. New. A half is equal to the measure, the fraction half or the number half. Fraction or number is the same thing. Fraction is equal to the measure of the ratio. That line, like that, okay? And then to, oh my goodness, can I not grab the damn line? To that, okay, to that. So, doesn't matter. So here we go again. So this is a ratio, okay? So half means the measure of this ratio. This is the antecedent, the consequent. So we turn to the abstract unit when we want to talk about numbers, right? Because this is defined in terms of the abstract unit. So here, our abstract unit is divided into two equal parts. And the number is the enumeration from those equal parts. It's only one. Therefore, the number is a half. Okay. So you write P over Q if and only if the measure of P colon Q is P over Q. All right. In no other case do you write that. So the students are understanding that correctly. And then we have here that they say the student focused her attention on the symbol of fraction without realizing that in order to be a rational number, its terms must be integers. That is bullshit. Its terms don't need to be integers. For example, 3.15 over 6 over 1.414 is a rational number, and these are not integers, okay? They're not integers. They're composed of integers and parts of integers. So obviously not carefully thought out, and it's common because mainstream morons do that. They don't know what they're talking about. So the next thing the author says is that the student identifies a simple symbol of the root with an irrational number. I think he's lying there, by the way. I can't possibly imagine why any student would think that square root 4 is an irrational number. Okay, can't imagine that. Now, if he had written square root 7 or something else, perhaps the student would have said because it has a root. Okay. So I think he's lying. And then he says distinction among several types of numbers remains muddy, each time depending on their semiotic representations. What's a load of BS? I mean, the symbols are clear, and even the dumbest students would not get this wrong. So then the question is, which is the exact quotient of the division 5 divided by 7? Well, the exact quotient is 5/7. Okay, that's the exact quotient. You don't have to convert it into a decimal representation because that's not more of a quotient than 5/7. Okay, and I think that somehow later on they tend to come to that same conclusion. So, in other words, if you read further on, that's what it means. Okay, so they're actually agreeing with me on that, which is kind of strange because most people don't really know that. So we continue down the research all the way to conclusions. Let's just see here, and I'm going to stop soon. So where are the conclusions? Here. So the understanding of irrational numbers is fundamental for students in reestablishing and extending the notion of numbers. That's absolute rot. I mean, you define numbers in terms of ratios, and you define irrational numbers, bullshit concepts, without ratios. How does that make any sense? Okay, so you see, a well-formed concept is usually defined in terms of attributes it possesses, not those that it lacks. It doesn't help saying any rational number is not one that can be written as P over Q, and then ask a student why pi over 4 is not a rational number. Well, pi is actually just a constant, and that's how it's used. Okay, so there's no difference in the way that the constant is used, even though it doesn't have a measure, an exact measure. Okay, so when students use this, they use some approximation for the constant, either 314 over 100 or 22 over 7 or whatever else you like. I don't care. So that's the understanding that they have, which is wrong, and they carry on till the end of the paper, BSing, reaching the wrong conclusions, wondering then why it is that students are struggling to understand mathematics, not being able to progress and reach a profound depth. Now, if you want to understand more, what you need to do is you need to become a subscriber to my channel. Okay, this channel here, the new calculus channel. Okay, become a subscriber. Go to any one of my videos, click on the video, and then there's a little join button when you play the video. If you join for $4.99 a month, you'll have access to all the information that I normally don't share with the public. You'll also have access to my books and my ongoing research. So while these books are sold to those who are not members, so you'll pay almost $10 for this book if you're not a member. But if you're a member, you'll have access to the book and its updates freely, and all the other books that I've written. Okay, so all of them are incredible books, which you need to study very carefully if you want to have a great mathematical future. So follow me on YouTube and on academia.edu. Click like, tell your friends about this, and hopefully I'll be chatting with you soon. I'm John Gabriel, and this is a New Calculus channel. Till next time.